Hello students, welcome to Vyas Edification Kota. In this series of NCERT discussion, it is time to continue further with Mathematics class 12th, and we have been dealing with the chapter Application of Derivatives. Time to move on to the exercise number 6.2. Exercise number 6.2 is based on increasing and decreasing nature of functions. We'll have to check whether a function is increasing or decreasing in an interval. We'll have to identify some intervals in which the function is increasing. The given function may be increasing or may be decreasing. Other than that, you will also need to check whether the function is increasing or decreasing at some particular point. So, a lot of theorems are given in the text before this exercise, and those have to be dealt with very carefully. If you read those theorems and practice questions on them, you will not find any difficulty in going through this exercise. Here, we will be discussing each and every question from exercise number 6.2, beginning from the first one. Let's talk about the first question. The first question says, show that the function given by fx equals 3x plus 17 is increasing on R. Now, if a function has to be proved that it is increasing on R, we'll have to prove that it is increasing in any interval throughout R, or for that matter, you can simply use the derivative test. Yes, derivative test is pretty simple. What you do is you find the derivative of function fx and check the sign of that function, that derivative, in the given interval. The given interval here is R, right? So we'll begin with that idea, and let's see. Fx is equal to 3x plus 17. This is given, right? So can we find the derivative of f? Yes, f prime x will be equal to simply 3. The derivative of 3x is 3, the derivative of 17 is 0. And this 3, you can observe that this is greater than 0. This is greater than 0 implies fx, since this derivative is greater than 0 for all x belongs to that given interval R. Therefore, fx is increasing. The symbol is for increasing for x belongs to R. All points in this interval, at all points in this interval, the function fx is increasing. That's what you can observe over here. Moreover, since this is always greater than 0, this is never 0, you can say that this function is strictly increasing as well. You can say that this is strictly increasing as well, right? That is all in this question. Let's move on to the next one. The question 2 says, show that the function given by fx equals e power 2x is increasing on R. Now, idea is similar to the first question that says that if you want to prove that fx equals e power 2x is increasing in this interval, let's find the derivative and check the sign of derivative in this interval, right? If the derivative is throughout positive, greater than equal to 0, then you can say that the function is increasing. If the derivative is greater than 0, then you can also say that the function is strictly increasing, right? Had the derivative been negative, less than 0 throughout R, you could have said that the function is decreasing. Let's check the derivative over here for the given function fx. This is e power 2x, right or not? Yes. Let's find the derivative. F prime x, the derivative of e power 2x would be e power 2x times 2. Will it be? Yes. This is the derivative. The derivative of 2x will be here, 2. You're applying the chain rule basically. That's what we have done. This is 2 times e power 2x. Now, do you have any idea about the values of e power 2x? First of all, let's take get some idea about the values of e power 2x. What I would like to draw is the graph of y is equal to e power x first. Or you can directly draw the graph of y is equal to e power 2x, will not make much difference. E power x and e power 2x are similar graphs. This is a kind of graph of e power 2x. This point is 1, this is 0, right? E power 0 will be 1 and throughout the function will be increasing. If you want to apply some graphical transformations, you could have done that as well. Let's see, if you wanted to draw e power 2x with the help of e power x, what will happen is all values on the x-axis will be divided by 2, and therefore the graph will actually, you can say that at the point previously, the point 1, wherever it was, that point has now shifted to 1 by 2 actually, okay? And so the graph has contracted. But this is e power 2x for us. For now, this is e power 2x. And can you check that y is equal to e power 2x is always greater than 0. This is always greater than 0. This is never 0, never touching the x-axis, right? So this is always greater than 0. Therefore, on the basis of this, can I comment that 2 times e power 2x is greater than 0 for all x belongs to this interval R? Yes, we can comment that. Okay. And once we have done that, therefore, f prime x is greater than 0 for all x belongs to real, which implies that this particular thing tells me that fx is increasing for x belongs to this. For this interval, the function fx is increasing continuously. That's what you can comment on the basis of this, right? This is something extra which we needed, on the basis of which we have commented the nature of the function very easily, right? Keeping this in mind, yes, that's all for this question. Let's move on to the next one after this. The third question says, show that the function given by fx equals sin x is increasing in this, decreasing in this, neither increasing nor decreasing in this, right? That's what the person says. Now, sin x is, you can observe sin x is not a very difficult thing. This is a pretty simple one. Can I do it with the help of simple graph, right? A simple graphical approach would also suffice, but then we'll also use the analytical approach, since NCERT people love the analytical approach, right? But let me draw the graph for y is equal to fx sin x. Fx equals to sin x. So this is the function sin x. This is 0, this is pi, this is 2 pi. This here is pi by 2. Okay, this is the peak, this here is 1. Do you observe that the function is continuously increasing from 0 to pi by 2? Then after that the function is decreasing from pi by 2 to pi. Can you observe that? Yes, that's what the person is saying. And since the function is increasing as well as decreasing in this interval 0 to pi, you can say that it is neither increasing nor decreasing in this interval, right? This is the graphical approach. If you can draw the graph, this is okay. But then no, that's not sufficient from the point of view of NCERT. Let's see. Let's begin with function fx equals sin x, the analytical approach. So we'll have to find the derivative of this. Yes, let's find the derivative. F prime x is equal to cos x. The derivative of sin x is cos x, right? And once you have noted that f prime x, the derivative is equal to cos x, can you identify the sign of cos x in different intervals? Yes, maybe. For the first part A, what do we have? X belongs to 0 comma pi by 2. In this interval, what will the values of cos x look like? So cos, the graph of cos, as you may observe, the graph of cos moves in this manner. This point is pi by 2, this is pi, this here is 1, this is 0, and this will be minus 1, the lowest point. The highest point will be 1. From 0 to pi by 2, you can observe the value decreases from 1 to 0, but it is always positive, right? For x belongs to 0 comma pi by 2, we know that cos x is greater than 0 and less than 1 as well. Cos x lies between 0 to 1, right? That's what we can observe. But is that all? You can actually write it as this, that 0 is less than cos x is less than 1. We are only interested in this part, by the way. We are not interested in less than 1 because greater than 0 suffices, right? So for x belongs to this, 0 is less than cos x is less than 1, or you can say that cos x is greater than 0. Therefore, the derivative of function f prime x, the derivative function, that is f prime x, is greater than 0. So what can you comment about fx? Since f prime x is greater than 0 in this interval, for x belongs to 0 comma pi by 2 in this interval, therefore you can say that fx is increasing for x belongs to 0 comma pi by 2. And this is what we started with wanting to prove, right? We had to prove, show that the function is increasing in this interval, and yes, that's what we have proved over here. Is that okay? Yes, this is something which we have done. Now let's talk about the second part after that, part B. Part B says that the function is decreasing in pi by 2 comma pi. How will we handle that? Let's take a look at this one, the second part. So for the second part, once again, let's see that the function fx is sin x, and so the derivative of this function will be simply cos x, okay? And what about the values of cos x in this interval? Part B, for x belongs to pi by 2 comma pi, you can see the graph of cos x. The graph of cos x is this, right? From pi by 2 to pi, the values will be from 0 to minus 1, right? So this gives me cos x is less than 0, greater than minus 1, or you can say that f prime x, cos x, that is f prime x, is less than 0. And since f prime x is less than 0, this tells me that fx is, what do you call this? Fx is decreasing in x belongs to, or you can say for x belongs to pi by 2 comma pi. Fx is decreasing for pi by 2 comma pi. That's what we wanted to prove, right? That's the complete proof of this one. The second part. For the third part, once again, for the third part, what do we need? We need the sign of the derivative, right? So, for x belongs to 0 comma pi, we know that cos x belongs to minus 1 comma 1. This is what we are aware of, right? This is what we know. Cos x belongs to minus 1 comma 1. Okay. Since cos x belongs to minus 1 comma 1, so we can comment about the derivative, that the derivative will also belong from minus 1 to 1, right? This tells me that f prime x belongs to minus 1 comma 1. Okay. And can you observe that the derivative is negative as well as positive for this interval, right? Implies f prime x is greater than 0 or less than 0 for different values in this interval, for x belongs to 0 comma pi, and on the basis of this, you can say that the function fx is neither increasing nor decreasing in this interval. That is what you can comment, right? That's a proof of this third part as well. That's a complete solution of this question, as you can see. Let's move on to the next one after this. The fourth question says, find the intervals in which the function f given by fx equals this is increasing or decreasing. Let's talk about the intervals. So for finding the intervals, we'll have to deal with derivatives once again, and let's begin with function fx is equal to 2x square minus 3x. This gives me f prime x. The derivative of x is 4x minus 3, right? The derivative is 4x minus 3. And now let's talk about part A, increasing. So for increasing, what do we need to check? For increasing, the derivative f prime x should be greater than 0. This is what we need, right? For increasing function, this is what we need, which gives me 4x minus 3 greater than 0, or this tells me x is greater than 3 by 4. So the interval in which the function f given by this is increasing will be, therefore, fx is increasing for x belongs to 3 by 4 comma infinity. That's what you can say, right? X belongs to 3 by 4 comma infinity. You can say the function is increasing in this way. Next, the part B says, find the intervals in which the function is decreasing. Okay. For decreasing, what do we need? We can say that the function fx, we have already found f prime x. For decreasing, f prime x will be less than 0. That's what you can say. Okay. And on the basis of this, what can you comment? What can you comment about this? This tells me that 4x minus 3 is less than 0, and this tells me x is less than 3 by 4. Is that okay? Yes, that's pretty simple. Therefore, fx is decreasing. Decreasing for x belongs to minus infinity comma 3 by 4. This is what you can comment. And yes, this is part 2 answer, this is part 1 answer. By the way, there is one important thing to note in this question over here. And what is that important thing? That important thing says that here you are asked increasing, and for increasing we simply say, okay, f prime x is greater than 0. You could also have taken f prime x to be greater than or equal to 0, since increasing simply says that the derivative should be greater than or equal to 0. Whereas this is a condition which is more strict, yes. So this is for strictly increasing, yes. This is ideally for strictly increasing, but then the NCERT people are lovely people, and Yeah, this is what they want from us. For increasing also, they want you to find f prime x greater than 0. If you find f prime x greater than equal to 0 as per the theorems given in the NCERT, it will not be wrong as such, and you'll get a closed bracket over here, maybe 3 by 4 will be closed 3 by 4 to infinity, the function will be increasing. Here, for this interval, you can say that function is strictly increasing. Similarly, for this, you can also say that the function is strictly decreasing, right or not? Yes. And that is all that is important in this question over here. Let's move on to the next question after this. The fifth question says, find the intervals in which the function f given by fx equals this is increasing or decreasing. Let's try to handle this one. And how do we do that? We'll find the derivative of function fx. The function fx is this, 2x power 3 minus 3x square minus 36x plus 7. And what's the derivative of this function? The derivative will be equal to 6x square minus 6x minus 36. This is what I am getting, right? We can take out a factor of 6 common and write it as x square minus x minus 6, which gives me 6 times. Let us split the middle term and factorize this expression. So 6 can be written as minus 6 can be written as minus 3 plus 2. So x square minus 3x, we can write it as x square minus 3x plus 2x minus 6. And what will that give me? X will come out common from here. One factor will be x minus 3 and the other factor will be x plus 2. That's what you can observe, right? So 6 times x minus 3, x plus 2, that's the complete factorization of this. And now, when we want to analyze in which intervals the function fx is increasing, then let's talk about this. For increasing, this is first part, right? So for increasing, f prime x should be greater than 0. That's what we note, right? And this implies that 6 times x minus 3 times x plus 2 should be greater than 0. And yes, you can apply the concepts of wavy curve, and therefore on the basis of this you can comment that critical points are minus 2 and 3. The sign will be positive, negative and positive in different intervals. That's what you can comment. So this tells me that fx is increasing for x belongs to minus infinity comma minus 2 and separately, and the other interval will be 3 comma infinity. The derivative is greater than 0 for these values of x which are less than minus 2 and values of x which are greater than 3. So the function is increasing for this interval and this interval. These are the different two intervals of x. Right. Let's talk about the part B, decreasing. The person says that f prime x will be less than 0, and this tells me that 6 times x minus 3 times x plus 2 will be less than 0 on the basis of that. This is derivative, right? Once you note this, therefore you can say that x belongs to minus 2 comma 3 is the interval in which the function will be decreasing. For decreasing, this is the answer. For increasing, this is the answer. This and this, right? That's the complete solution of this question over here. Yes. Let's move on to the next question after this. The sixth question says, find the intervals in which the following functions are strictly increasing or decreasing. There are some parts of this question. And find the intervals in which the following functions are strictly increasing or decreasing. That's what we are supposed to find. Okay. So this function fx, let's call this fx equals x square plus 2x minus 5, which gives me f prime x is equal to 2x plus 2, which is 2 times x plus 1. Can you note that? Yes. And mark the critical point. This is minus 1, right? Here the function will be, here the derivative will be positive, here the derivative will be negative, and on the basis of this you can say that fx is strictly increasing for which values of x in this interval? For x greater than minus 1, or which can be written in this interval, in the interval format as, which can be written in the interval format as for x belongs to minus 1 comma infinity. Okay, this is what you can comment for minus 1 comma infinity. And similarly, fx is strictly decreasing for what? X belongs to less than values, less than -1 values, that is minus infinity comma -1, and you have open brackets. This is the final answer for this part over here. Let's continue further and see the second part of the sixth question. And what does that say? That says that we have to check this function and similar thing for this function, that is increasing, strictly increasing and strictly decreasing. So let fx is equal to 10 minus 6x minus 2x square. Okay, so this tells me that f prime x, the derivative, will be equal to 0 minus 6 minus 4x. This is what you will get, right? The derivative of 10 is 0, this is minus 6 and this is minus 4x. You can take out something common from here, you can take out minus 2 common from here, and this will be 2x plus 3. Please note that this is minus 4x minus 6. Yes, this is 2x plus 3, and the critical point is 3 by 2 with a minus. The critical point is minus 3 by 2, as you can note from here. This is the point where f prime x is equal to 0. Okay, so beyond this, in this interval, you can observe that this will be positive, but overall value will be negative, and here the overall value will be positive. Therefore, fx is strictly increasing for this interval over here, that is x belongs to minus infinity comma minus 3 by 2. This is what you can note. Fx is strictly increasing for this, fx is strictly decreasing for x belongs to, what you can say is strictly decreasing minus 3 by 2 to infinity. This is what you can comment. This is minus 3 by 2 comma infinity. That's what you can say, right? This is the final answer for this question over here. Let's see the third part after this. The third part, C part, says check this function. Okay, in the C part, this is given. Let fx equals minus 2x power 3 minus 9x square minus 12x plus 1. This is what we have. Okay, and this tells me that f prime x, the derivative of fx, will be minus 6x square minus 18x minus 12. Do you see that a factor of 6 with a minus will come out common from these terms, and what will remain is x square plus 3x plus 2. Okay, let's factorize this. Let's factorize this using splitting the middle term. This can be done as 2 times 1. This is 2 plus 1, right? So x plus 2, x plus 1. This is the factorization of this, right? And can you note that f prime x will be 0 at x equals to minus 1 and x equals to minus 2, right? At minus 2 and minus 1. Okay, so for values greater than minus 1 in this interval, for x, let us say you can take x equal to 0, for example. X equal to 0 will imply this is positive, but this is negative. So overall factor will be negative. For this interval, you will have, let us say 1.5, minus 1.5. This will be negative, this is positive, negative. Negative and negative will become positive. Okay. For values less than minus 2, let's suppose minus 3. This is negative, this is negative, this is also negative. Overall negative. This is what you'll see. And therefore, fx is, what you can comment, strictly increasing for x belongs to, strictly increasing for this interval where the derivative is positive, minus 2 comma minus 1. And you can also say that fx is strictly decreasing for, strictly decreasing for this interval over here, this and this. So fx is strictly decreasing for x belongs to minus infinity comma minus 2 and minus 1 comma infinity. These are the intervals for which the function fx is strictly decreasing. This is the interval for which fx is strictly increasing. This is part C. Let's see the part D now. The part D says 6 minus 9x minus x square. This is the next function that we have. Okay, we are supposed to check the similar thing. So let fx equals 6 minus 9x minus x square. Okay, this is not 9. This is 6 minus 9x minus x square, and this gives me f prime x is equal to 0 minus 9 minus 2x. Okay, I can take out a factor of minus common from here, and what will remain is minus of 2x plus 9. Okay, the critical point, as you can observe, is minus 9 by 2, where this derivative is 0, right? 2x plus 9 equals 0 implies x equals minus 9 by 2. And for values beyond this, in this interval, this is positive, but this is negative. Here, the sign will change, right? This is what you get. And therefore, you can comment that fx is strictly increasing for x belongs to which interval? Strictly increasing over here, that is minus infinity comma minus 9 by 2. You can also say that fx is strictly decreasing x belongs to this interval, which is minus 9 by 2 comma infinity. This is what you can comment, and that's the complete solution for this part D. Let's discuss part E next. This is part E. What does it say? X plus 1 whole power 3 and x minus 3 whole power 3. This is the function. Okay, that's an interesting one. Let fx be this function. X plus 1 power 3, x minus 3 power 3. Let fx be this function. Okay, this gives me that f prime x will be equal to what? F prime x will be equal to, you'll have to apply the product rule first. Okay, let's keep this constant x plus 1 power 3 as a constant. Let's differentiate this. Okay, so differentiating this will be done with the help of chain rule. So this will be 3 times x minus 3 whole square, and the derivative of x minus 3, which is 1, which is pretty simple, right? The next term will be plus the derivative of this, keeping this constant, the derivative of this. So x minus 3 power 3 will remain as it is. Derivative of this will be 3 times x plus 1 whole square, and the derivative of x plus 1 will be 1. Now, can you factorize this derivative f prime x? Yes, you observe that x minus 3 whole square, x minus 3 whole cube, this can come out common. Similarly, x plus 1 whole square, x plus 1 whole cube, x plus 1 whole square can come out common from this term and this term. Another factor of 3 can also come out common. What we'll get is x plus 1 whole square, x minus 3 whole square, and in the bracket what will remain is x plus 1 over here times 1, and here what will remain is x minus 3. Okay, this is what remains, right? So let's simplify this further. 3 times x plus 1 whole square, x minus 3 whole square is what I'm getting, right? And what will this be? This is 2x minus 2, is it? Yes. This is 2x minus 2. Can be factorized further? Yes, we can factorize this further by taking out 2 common from here, and therefore this gives me f prime x will be equal to, you take out 2 common from here, 3 times 2 becomes 6, and this is x plus 1 whole square, x minus 3 whole square times x minus 1. Yes, is that so? Yes. And now the critical points will be 1, 3 and minus 1. Minus 1, 1 and 3 marked on the number line in this manner, right? Okay. For values greater than 3, let's take for example 4. This is positive, this is positive, this is also positive. Overall sign will be positive. For values between 1 and 3, let's take for example 2. This is positive. This is 2 minus 3, which is negative, but there's a square, right? So this also, overall this value becomes positive, 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 and 2 minus 1 is also positive. The overall sign is positive. Yes, you can comment on that. Okay, and what happens for this interval? Let's take x equals to 0. This is positive. This is being a square, this also becomes positive. And 0 minus 1, this is negative. So overall value is negative, I suppose, right? For values beyond minus 1 on this side, you have minus 2 for example. This becomes minus 2 minus 1, which is negative. Minus 2 minus 3 negative, square is positive. Okay, so negative into positive. This is minus 2 plus 1, which is negative, square is positive again. So negative, positive, positive will be overall negative. This is the sign scheme for the derivative f prime x. Okay, and on the basis of this, can you comment the intervals in which in which the following functions are strictly increasing or decreasing? Yes. Therefore, fx is strictly, the first part says strictly increasing in which interval? I see that f prime x is positive over here and over here. So, if x is strictly increasing in x belongs to 1, 3 and another interval, that is 3, infinity. This is what you observe, right? Is that okay? Yes. Next, you can say that strictly decreasing in which interval? Strictly decreasing implies you will have to note the sign of f prime x negative. So, you get the negative sign in this and this interval. Therefore, x belongs to minus infinity, minus 1 and x belongs to minus 1, 1. Those are the intervals in which the function fx is strictly decreasing. That's what you can note over here. Now, a small comment, I can add a small comment over here. Some texts, in some texts, okay, not the NCERT, but in some other textbooks, you may find that since the derivative is only becoming 0 at one particular point, yes. So, people may comment that strictly increasing for x belongs to 1, infinity will also be true in this case over here, okay, since this is a discrete point over here. That's what some texts may offer you. But from the point of view of NCERT, this is the final solution that we require. And yes, this is all that you have in this question over here. Let's move on to the next question after this. The question 7 says, show that y is equal to log of 1 plus x minus 2x upon 2 plus x for x greater than minus 1. Now, this x greater than minus 1 is required for defining this log, right? X plus 1 should be greater than 0. That is important. So, we'll only deal with this interval. Show that this is an increasing function of x throughout its domain. Okay. If this is an increasing function of x throughout its domain, then we'll have to check the derivative. Whether the derivative is always positive, that's the important thing that we need to check. And how do we go about doing that? That does not sound very difficult from the first look. Y is equal to log of 1 plus x minus 2x over 2 plus x, comma x greater than minus 1. This is what we have, right? Let's try to find the derivative of this. Dy by dx, okay, is equal to, the derivative of log something is 1 upon that, 1 plus x, and derivative of 1 plus x is simply 1, chain rule, right? Minus, what about this? Here we'll need the quotient rule. You observe that? We'll need the quotient rule, and quotient rule says denominator square. Denominator will be squared. This is 2 plus x whole square, and in the numerator what you'll get is denominator times the derivative of numerator, which is 2x, the derivative of 2x is 2, minus numerator, which is 2x, times the derivative of denominator, which is the derivative of 2 plus x, which is simply 1. This is what you'll get, right? Right? Yes, that's the complete derivative, dy by dx. What will this be equal to? 1 upon 1 plus x is what I get, minus. What is this in the numerator? Let's see. This is 4 plus 2x minus 2x. So, this becomes 4 upon 2 plus x whole square. Okay. Can we comment about the sign of this from here? No, not yet. Let's try to simplify this further and see where does that take us. Which gives me dy by dx is equal to, we'll have to take the LCM in the denominator, yes. So, this becomes x plus 1 and this is x plus 2 whole square, is it not? Yes, this is x plus 2 whole square. And what you'll have is x plus 2 whole square over here minus 4 times x plus 1 is what you'll obtain in the numerator. This is what you have crossing, right? Okay, next thing what you'll get is, this is x square plus 4x plus 4 minus 4x minus 4 upon x plus 1, which is okay, x plus 2 whole square, which is also okay, 4x goes, 4 also goes. Okay. So, now what remains is x square over x plus 1, x plus 2 whole square. This is derivative of y. This is derivative of y, and now at this stage, yes, Yes, at this stage we can comment about the sign of the derivative. Yes. Mark the critical points. The critical point -2, -1 and 0 are the critical points. Okay. But do you observe that since x is greater than -1, we are not supposed to go behind this. We are only supposed to deal with values on this part, not on this part, right? Okay. And once we have this particular thing in our mind, then let's analyze the values beyond 0 first of all. Let's choose any value beyond 0. Let's choose 1. For 1, this is positive. This is positive. This is also positive, so this becomes positive. Right? The sign is positive. For values between -1 and 0, let's analyze the values between -1 and 0. What will happen is, let's choose -12 for example. -12 plus 2 is positive. Positive square is also positive. -12 plus 1 is positive. That gives me a positive value. And -12 squared will become positive. So positive, positive, positive will be overall positive. Yes, this is what you get. Is that okay? Yes. And once we are through with this, therefore, on the basis of this, we can comment, therefore, dy by dx derivative is greater than 0 for all x belongs to -1 comma infinity. In this interval, you can say that function is increasing. Function is greater than equal to 0. You can say at this 0, the function will be equal to 0. So you can say that function derivative is greater than equal to 0 for all x belongs to this, which tells me that yes, the function is increasing throughout its domain. That's what you can comment, and that's the complete proof of this part over here. Is that all? Yes, that is all in this question. Let's move on to the next question after this. The next question says, question number 8 says that find the values of x for which y equals x times x minus 2. Okay, and there's a whole square is an increasing function. Okay, so we are supposed to find the values of x. Let's begin with this. Y equals x times x minus 2, and there's this complete whole square over here. Can I write it as x square times x minus 2 whole square? Is that okay? Yes. Now let's find the derivative. Y prime will be equal to what? We'll have to apply the product rule on this. The first function remains constant. Derivative of the second function will be 2 times x minus 2. X minus 2 derivative is 1. Plus x minus 2 whole square remains as it is. Derivative of x square is 2x. This is what I'll get. Is that okay? Yes. Once we are through with this, can we factorize this further? There's a factor of 2. There's x minus 2, x minus 2. So 2 times x minus 2 will come out common. And what will remain is 2x minus 2, x is gone, coming out common. And here you'll get x minus 2 as common. Okay. And this is 2 times x minus 2, which is okay. This is 2x minus 2. Okay. That's pretty simple up till now. Yes. We can take out a factor of 2 common from here as well. So this will be 4 times x minus 2 times x minus 1. And now, can you analyze the sign of this derivative? Yes, the critical points are 1, 2 and 0. 0, 1, 2. Okay. Let's analyze the values beyond this interval. Okay. For those of you who are aware of the wavy curve approach, you can say that this is plus, this is minus, this is plus and this is minus. But let's analyze the sign in each interval. For x greater than 2, let's pick up some value. Let's pick up 3. So for 3, this is positive, this is positive, this is also positive. So this becomes positive. Okay. For between 1 and 2, let's pick up some value, 1.5. This is positive, this is negative, this is positive. So there are plus, minus and plus, which will be overall minus. Between 0 and 1, the sign will be, let's pick up some value 0.5. This is positive, this is negative, this is also negative. So positive, negative and negative will be overall positive. For values beyond 0 on the left hand side, what we'll have, let's say you pick up minus 1. This is minus 2, which is negative. Minus 3 becomes negative and minus 1 is also negative. So negative, negative, negative will be overall negative. That's what you'll get. Okay. And the person has asked, find the values of x for which this is an increasing function. Therefore, fx is increasing. Fx is increasing for x belongs to, increasing implies that derivative should be positive. Derivative should be positive. 0 comma 1 and x belongs to 2 comma infinity. Those are the intervals in which the function fx is increasing. That's what you can comment. This is separate interval, right? 0 comma 1 in this interval, yes, the function is increasing. In this interval, the function is increasing. Mind you, I am using the word and, I am not using union, right? You cannot use union over here. You can only use and, right? Please take note of that and then you are good to go. That's a complete solution of this question. Let's move on to the next one after this. Question 9th says, prove that y equals 4 sin theta over 2 plus cos theta. There's a minus theta is an increasing function of theta in 0 comma pi by 2 in this particular interval. We are only dealing in this particular interval. So let's see where does that take us. We are given y equals 4 sin theta over 2 plus cos theta. Okay. Minus theta is also there. Can we find the derivative? Yes. We can find the derivative very easily maybe. How will we find the derivative? Derivative does not seem very difficult. Y prime, derivative y prime will be equal to what? Y prime will be equal to what? Y prime will be, in this you have quotient, right? So let's apply the quotient rule. You'll have denominator square in the denominator. Okay. Denominator, this is 2, in the numerator you'll have denominator times derivative of the numerator. Now what is in the numerator? You have 4 sin theta and the derivative of 4 sin theta will be 4 cos theta. Okay. Minus the numerator as it is, this is 4 sin theta times the derivative of the denominator. Derivative of the denominator, yes, 2 plus cos theta. The derivative will be 0 minus sin theta. So this is actually minus sin theta. Okay. Is that all? Yes. There's a theta as well. So you'll have a minus theta. Derivative, you're finding derivative with respect to theta. Okay. Don't make a mistake in that. Right. This is not derivative with respect to x. This is derivative with respect to theta. So you are finding dy over d theta, mind you. Right. This is what we are finding. So derivative of theta with respect to theta is this one. Okay. And what will this become? The denominator is 2 plus cos theta squared. Okay. In the numerator you have 8 cos theta plus 4 cos square theta and plus 4 sin square theta. Okay, that's simple. Yes, that's pretty simple. And then you have a minus 1 as well. Yes, you have a minus 1 as well. 4 cos square theta, 4 sin square theta. You can take out a 4 common and what will remain is cos square theta plus sin square theta, which is simply 1, right? So this is 8 cos theta plus 1 over this 2 plus cos theta whole squared and there's a minus 1. Now can we comment about the sign of this directly? No. This minus 1 is creating an issue for us. Let's take the LCM and simplify this further. Where does that take us? This is dy by d theta is equal to what? This is equal to what? In the denominator you will have 2 plus cos theta and its square. Yes. In the numerator you have 8 cos theta plus 1 minus of 2 cos theta wholes, 2 plus cos theta whole square minus of this is 2 plus cos theta squared. This is what you have, right? This is what you have and this will become 8 cos theta plus 1 minus, let's square this term. This is 2 square is actually 4 and did we miss a 4 somewhere? Yes, this is not 1, this is 4 over here. Oh, this is 4, yes, this is 4 and this is 4 therefore. Don't make a mistake over there. This becomes minus 4 minus cos square theta minus, what is this? 2 times 2 is 4 cos theta. This is what remains. In the denominator you have 2 plus cos theta and its square. Now let's see the numerator and analyze it. You have minus cos square theta, okay, and your 4 minus 4 is gone, okay, minus cos square theta and what else? 8 cos theta minus 4 is what I have. So this will become 4 cos theta, okay, 2 plus cos theta squared is also there. Can you take out something common from there? Yes, you can observe that cos theta will come out common in the numerator. Okay, and what will remain is, what will remain along with this is minus cos theta plus 4 or 4 minus cos theta will remain. 2 plus cos theta times this. 2 plus cos theta whole square is what I have over here. Okay. Now, can you analyze the signs of these terms over here? Yes, let's try to analyze the sign for this interval, for this particular interval over here. Theta in this interval, 0 comma pi by 2. Observe that cos theta is between 0 and 1, so this will be positive. This 4 minus cos theta will be also positive. This 2 plus cos theta is also positive because cos theta is always less than 4, right? And 2 plus cos theta will be positive anyhow, that's not an issue. So this is positive, this is positive, this is positive, so this is greater than 0. This tells me that dy upon d theta is greater than 0 for x belongs to 0 comma pi by 2 in this interval. Yes? At max at pi by 2 this will become 0, so you can say this is greater than equal to 0. For pi by 2 this will become 0. Rest all will be still positive. And therefore, since this is greater than equal to 0, this tells me that y is increasing function in this interval, mind you. Y is increasing function in this interval. That's what you have proved. That's what you wanted to prove, right? That's a complete solution of this question. And let's move on to the next one after this. Question 10th says, prove that the logarithmic function is increasing on 0 comma infinity. Now, what is the logarithmic function? The logarithmic function is not difficult. We are talking about y is equal to log x, right? We are talking about this. What's the base? Base is e, the Napier's base, right? And the condition on this is that x will be greater than 0. X has to be greater than 0, right? Okay. X is greater than 0. On this interval, this is a domain, right? Anyhow. So we can find the derivative. Derivative is 1 upon x. That's a derivative, right? Okay. If you are aware of the derivative, then what can you comment about this particular thing further is that logarithmic function is increasing since x is greater than 0, therefore 1 by x will be greater than 0. That's what you can observe, right? Since x is greater than 0, therefore 1 by x will also be positive. That's what you can comment. And derivative, which comes to be derivative is greater than 0, and this implies that y is increasing function for x belongs to this interval 0 comma infinity, greater than 0, right? That's a complete proof. A very simple and silly question. Over here, the only thing is which is important is you should be aware of logarithmic function, and that's all that is important over here. Rest all is pretty simple, right? Can you also draw the graph of logarithmic function? Yes, graph of logarithmic function is not a difficult thing. Y is equal to log x base e. The graph looks like this, right? And this will be this. This is 1, this is 0. For x greater than 0, it is defined only for x greater than 0, and you can see the function is increasing and increasing and increasing and increasing throughout, right? That's the complete solution of this question over here. Let's move on to the next one. Question 11 says, prove that the function f given by fx equals x square minus x plus 1 is neither strictly increasing nor decreasing on minus 1 comma 1. Let's see. Let's check the function, right? X square minus x plus 1. Now, for those who are aware of the graph of this function, the graph will look something like this. X square minus x, right? That's what you have. So, minus b by 2a would be this, and the graph will look something like this. This point is 0, this point is 1, and this least point will be 3 by 4. Okay, the graph is be parabolic. Okay. In the interval minus 1 to 1, you can observe that the function will be increasing. Here, I am drawing a dotted line, but this is the region I am talking about, right? The function will be decreasing up till here, up till the point 1 by 2, and the function will be increasing. This is directly by drawing the graph. That's what you can comment. Oh, how did you draw the graph? I drew the graph using concepts of parabola, right? Parabola, yes, the quadratic graph is pretty simple. You can find the vertex easily, and upward facing parabola can be drawn. Vertex will be minus b by 2a minus d by 4a. D is the discriminant. This is a graph of y is equal to x square plus bx plus c. For a greater than 0, the graph will be upward facing. Yes. For a less than 0, the graph will be downward facing, and the vertex v will be exactly same. Minus b by 2a comma minus d by 4a. The values will take care of themselves, and this is what you get. Right. So minus b by 2 is very simple, and minus d by 4a, where d is the discriminant, that is b square minus 4ac, can be found easily, and I can comment about the graph, right? There's something which is there, but here, this will not do. You also need the analytical approach, and what does the analytical approach say? So fx is x square minus x plus 1, right? Can I find the derivative f prime x? Yes, this is equal to 2x minus 1, okay. So the critical point, as you may observe, is 1 by 2. 1 by 2 is the critical point. Yes, 1 by 2 lies between 1 and minus 1, okay. Beyond 1 by 2, what will happen is, beyond 1 by 2, this will be a positive value. This is positive. And before 1 by 2, this will be negative actually, yes. And you may observe that f prime x is greater than 0 for x belongs to 1 by 2 comma 1 when we are talking about this interval, and f prime x is less than 0 for x belongs to minus 1 comma 1 by 2. That's what you can observe from here, right? This tells me that f prime x is greater than 0 and less than 0 both implies fx is increasing in some interval and decreasing in some other interval, implies fx is neither increasing nor decreasing function in this interval, right? Fx is neither increasing nor decreasing function. That's what you can say in the interval minus 1 comma 1. Right? Since it is sometimes increasing and sometimes decreasing, therefore it is called a neither increasing nor decreasing function, as you can see behind me over here. That's the complete solution of this question. Let's move on to the next one after this. The question 12th says, which of the following functions are decreasing on 0 comma pi by 2? Okay. So for 0 comma pi by 2, what can we say? Can we draw the graph and comment about the functions? Yes, we can draw that. Which of the following functions are decreasing? Now cos x is pretty simple. Cos x will be this. For 0 and pi by 2, cos x is something that we are aware of, right? This is for part A. Okay, and this is a decreasing function, that's not an issue. Part B says cos 2x. Now the graph of cos 2x. For drawing the graph of cos 2x, first we draw the graph of cos x and we divide all values on the x-axis by 2. So I am drawing up till pi. This is pi by 2 and dividing by 2 will be pi by 2. Pi by 2 by 2 will be pi by 4. This is 0. Right? This is the graph. Okay. This is the graph of this function y is equal to cos 2x. This is the graph of y is equal to cos x. Okay. Okay. And okay. And you may observe that this function is decreasing. Yes. This function is also decreasing. What about part C? In part C, you need cos 3x, and cos 3x can also be drawn with the help of a similar idea. All values on the x-axis will be divided by 3. Okay. So pi by 2 will become pi by 6, pi will become pi by 3, and 3 pi by 2 will become pi by 2. And we are interested in the interval 0 to pi by 2, right? We are interested in this interval. The function decreases and the function increases after this point. So function is neither increasing nor decreasing, as you can see in the interval 0 comma pi by 2. So this is not done. Okay. What about part D? In part D, we have to draw the graph of tan x. The graph of tan x, just a minute. The graph of tan x is this. For pi by 2, 0 to pi by 2. Beyond this, it goes in this manner. Okay, and after this also, it has this kind of a shape. But we are interested in 0 to pi by 2. You can see the function is increasing throughout. It is not decreasing. So, decreasing? No, it is not decreasing. That's not the answer. So, options A and B or parts A and B are correct. But this is the graphical approach. Do you have an analytical approach as well? Yes, we have an analytical approach as well. So, part A, let fx is equal to cos x, which gives me f prime x is equal to minus sin x. Okay. And what can you comment about the values of minus sin x and 0 comma pi by 2? This is less than 0 for x belongs to 0 comma pi by 2 in this interval. How do you know that? Because I know the values of sin x are this 0, pi. I can comment about the values of sin x on the basis of this. This is pi by 2, right? From 0 to pi by 2, the values are in positive, therefore minus sin x will be negative. And for x belongs to 0 comma pi by 2, this is less than 0, implies fx is decreasing function. Okay. For part B, we have let fx equals cos 2x. Okay, fx equals cos 2x. Okay, then we can find derivative f prime x. What will that be? Minus sin 2x times 2. Derivative of 2x will be involved over here. Okay, and values of sin 2x. What can you comment about the values of sin 2x? This is 0, this is pi. You will have to draw the graph again. This is pi by 2, sorry, pi by, yes, this becomes pi by 2 over here. This is pi by 4 now, and the values are greater than 0, the values are positive. Therefore, this is positive with a negative, this becomes less than 0. And for x belongs to 0 comma pi by 2, this is less than 0. This implies that function fx is decreasing in the interval this. Fx is decreasing in the interval this. And this is how you can analyze option A and option B. Part A and part B, these are decreasing functions. The remaining two, as we have solved over here, we can solve using this approach as well. And I think we can leave it up to you for that matter. This is the complete solution of this question over here. Let's discuss this question next. Question number 13 says, on which of the following intervals is the function f given by fx equals x power 100 plus sin x minus 1 decreasing? On which of these intervals is this function decreasing? And how are we going to deal with this? Let's see, fx is given to be x power 100 plus sin x minus 1. This is what fx looks like. So, the derivative of fx, that is f prime x, what will this look like? This is 100 x power 99 plus derivative of sin x is simply cos x. Okay. Now, if you observe, x and cos are two different types of functions altogether, and actually finding a 0 will be very difficult for this particular case. So, what do we do in this case? We are not supposed to worry too much because we are given certain intervals, right? And we are supposed to check values within those intervals, values of this f prime x. Yes, let's check for option A, x belongs to 0 comma 1. In this interval, do you observe that 100 x power 99, this particular quantity will be greater than 0. Yes, this is a positive quantity. This x is positive, therefore x power 99 is positive. Multiplying by 100 will also give me something positive. What about cos x? Now, if you take a look at cos x, the value of cos x in this interval, now this x is in radians actually, this x is in radians. And in terms of radians, when I talk about 1 radian, do you observe that 1 radian is approximately somewhere around 57 degree, right? So, it is still in the first quadrant, right? All of these values lie in the first quadrant. So, cos x is also greater than 0. Okay. You can observe that in f prime x, this is positive, implies this is greater than 0. Overall, this is greater than 0 since this is positive and this is positive. Therefore, we can say that f is increasing. Okay, f is increasing. But we were looking at decreasing. We were looking for decreasing. Okay, so A is not the correct answer. Okay, let's talk about option B then. In option B, we have x belongs to pi by 2 comma pi. Okay, so now we are talking about the second quadrant. Okay, and fx is equal to 100 times x power 99 plus cos x. Do you observe that cos x in the second quadrant will lie from 0 to minus 1, or alternatively from minus 1 to 0. This value lies from minus 1 to 0. That's one thing. What about this value over here? Now, if you take a look at 100 times x power 99, what will this value be? X is greater than this pi by 2. And pi by 2, pi is 3.14, pi by 2 is 1.57, which is greater than 1, right? So, greater than 1 multiplied by 100, this quantity will be anyways greater than 100, yes or no? Yes. Even if you add -1 to this quantity, by the way, this would be very, very huge. This would be even more greater than 100. This will start somewhere around 157 and reach up till 314 by multiplying with this. Oh, no, we also have exponent 99. Oh, this is even bigger, even bigger. This is 1.57 raised to power 99, which is a very huge number, and then you'll multiply that by 100. This is very, very big as compared to 100. Even if you subtract 1, you will get a positive quantity, right? So this is always positive. Okay. That implies in this interval, the function f is increasing again. The function f is increasing again. Okay. So we were looking for decreasing. No, this is also not the answer. We are left with only option C and D. Now option C, we have 0 to pi by 2. Let's check. Let's check option C next. X belongs to 0 comma pi by 2. Okay. Now this option is similar to this one because this is the first quadrant. Cos x will be positive and this is also positive, right? This is also positive. So this gives me f prime x is greater than 0. Okay. Again the function is increasing. Okay. The function is not decreasing in any of these intervals, right? The function is increasing in A, B and C. On which of the following intervals the function f given by this is decreasing? None of these options is correct. Therefore, option D is the correct answer for this question, as you can clearly see over here. The 14th question says, for what values of A, the function f given by fx equals x square plus ax plus 1 is increasing on the interval 1 comma 2. This is the interval and we are supposed to see on for what values of A the function given by this is increasing. So fx equals x square plus ax plus 1, okay, and we'll be dealing with the derivative, right? So f prime x is equal to 2x plus a. This gives me this. This particular quantity should be greater than 0 for x belongs to 1 comma 2. This is what we want, right? And as you may observe, a is just a quantity, constant quantity. 2x is a positive number. This function, this f prime x, for that matter, this f prime x is what kind of a function? If you observe carefully, maybe we can take a look at the second derivative, but this is the straight line. This is a straight line graph having slope 2. So this graph will move in this way, right? Least value in the interval 1 comma 2. In the interval 1 comma 2, the least value will be at 1. The greatest value will be at 2. For this is a graph of y is equal to f prime x. I am looking at the graph of y is equal to f prime x. Okay. So, for making this value positive throughout this interval, what do we need? The value at x equal to 1 of f prime x should be greater than 0. This is the important thing. This will automatically be greater than 0 because anyways this is greater than this. That's what you observe. So, the important thing to note over here is that f prime 1 should be greater than 0, and what does that give us? That gives me 2 times 1 plus a should be greater than 0, and that gives me a should be greater than minus 2. That is my required answer for this question. That's pretty simple, yes. For what values of a the function f given by this is increasing? These are the required values of a. The interval, as you may note, is minus 2 comma infinity. That's the interval, right? A belongs to this. For a belongs to this, the function is increasing, as you can see. Is that all? Yes, that's all in this question. Let's move on to the next one after this. Question number 15th says, let I be any interval disjoint from minus 1 comma 1. Okay. Prove that the function f given by this is increasing on I. Okay, let's take a look at this interval. So, disjoint from minus 1 comma 1 would imply that this particular region should not lie in that interval, right? Okay, let I be any interval disjoint from minus 1 comma 1, prove that the function f given by this. So, fx is equal to x plus 1 upon x. This is what we have. Okay, so what about f prime x? F prime x will be equal to 1 minus 1 upon x square, which is simply equal to x square minus 1 upon x. And for analyzing the sign scheme, let's factorize the numerator. This is what you get. Okay, the critical points minus 1, 0 and 1. That's what I observe. Okay, the sign of f prime x for values greater than 1 will be equal to what? For values greater than 1, beyond 1, you will have, let's take for example 2. This will be positive, this will be positive, overall will be positive. And we are interested in this values below, before minus 1. Let's talk about those values. Before minus 1, let's take minus 2. This is minus 2 plus 1. What will that be? By the way, this is x square in the denominator. Let's not make a mistake on there. This is minus 2. Minus 2 plus 1 will be negative. Minus 2 minus 1 will be negative. Minus 2 square is positive. So, negative, negative and positive will be overall positive. Okay. So, in this interval the function is increasing, in this interval the function is increasing. These are disjoint intervals from minus 1 comma 1. Yes. The important thing, the one more important thing, I will draw the graph of fx equals x plus 1 upon x in front of you. Okay, and how do I draw the graph of that? X plus 1 upon x. Now, if you observe, what does f y is equal to x look like? Y is equal to x is this line. What about y equals 1 over x? Y is equal to 1 over x is this and this curve over here, right? This curve which is decreasing, becoming very, very close to the x-axis, and that one, right? Let me erase this. This is not required. Now, once you know that graph, then the graph of x plus 1 upon x is similar to, is something like this. I'll explain that over here. Let me draw the second graph again, and this one. This is y is equal to 1 over x. Now, imagine adding these up. So, you begin with a 0 and very, very close to infinity value, and then this particular value decreases very fast, this particular value increases not so fast, but then it becomes very, very close to 0. So, the overall output somewhere around this point will be very, very close to this, right? That's what I observe. And both the values are positive. So, I'll be always above this line, and yes, this is the kind of shape that you will get. This is the kind of shape that you will get. If you observe, the derivative is 0 at this point and this point. Yes. The derivative is 0 at this point means this is the point at which the derivative becomes 0. The slope becomes 0 actually. This is 0.1. And the value of the function at 1 is 1 plus 1 upon 1, which is 2. This is the least value of this function when you consider values which are greater than 0. X-axis and y equals fx is what I am talking about. This is 0. Let's talk about values below, before x equal to 0. So, you have this line and this graph. Similar graphs will be obtained. Similar graph will be obtained over here in this manner, something of the sort. And this value will be minus 1. This point will be minus 2 over here. That's the peak on this side of the graph, right? That's the kind of graph that you'll get. Now, analyze the shape. Analyze the shape. From minus infinity to minus 1, the function is increasing. Then from 1 to infinity, the function is increasing. And if you consider any interval which is disjoint from minus 1 comma 1, you will observe that the function is increasing throughout. Function is increasing throughout if you analyze any interval, right? Is that okay? Yes. Any interval disjoint from minus 1 to 1. Okay. Is that all? Yes, that is all that you have. We have proved that this is increasing on the interval I. One very crucial thing which you should note over here is that we can take an interval can be taken on this branch only, an interval can be taken on that branch only. You can also take an interval which comprises of partly this branch and partly this branch as well. And for that interval also, if it is just disjoint from minus 1 to 1, the function will be increasing. Let's say I take from minus 2 to 2 except for this interval minus 1 comma 1. The function will be increasing throughout. The function will be increasing throughout. From minus 2, this function increases and then this function increases again up till 2. That's what you can observe. Any particular subset of that interval, the function will be increasing for this one, right? That's what you can observe from the graph as well. That is some extra bit of information which will be helpful for you, right? But otherwise, we've seen that this is positive, implies fx is increasing in this interval and this interval. This greatest value here and the least value here is bigger than this value, right? Therefore, the function is increasing in any interval which is disjoint from the interval minus 1 comma 1. That's all. That's a complete analysis of this question over here. And now we'll move on to the next question. The 16th question says, prove that the function f given by fx equals log of sin x is increasing on this and decreasing on this. So, we are interested in the function fx equals log of sin x. Let's talk about this. Log sin x. Okay. which gives me f prime x is equal to 1 upon sin x, and the derivative of sin x is cos x. Okay, we apply the chain rule. This is what I get, and this is actually equal to cot x. Cos upon sin is equal to cot x. Can you analyze the sign of cot x in these intervals over here? Yes, I can do that. This is 0, pi by 2, pi. For 0 to pi by 2, okay, do you remember the graph of cot x? Yes, you should remember the graph of cot x. This is the graph of cot x. This is pi by 2, and this is an asymptotic line. This is pi. Right? For 0 to pi by 2, the value is positive. For pi by 2 to pi, in the second quadrant, the value will be negative. Yes. So from here, you can analyze that f is increasing for x belongs to 0 comma pi by 2 in the first interval. F is decreasing for x belongs to pi by 2 comma pi. That's the second quadrant. Yes, this is what you can observe directly from here. That is what we wanted to prove, right? That's what we started with. This is a complete solution for this question over here. Let's discuss the next question. Question number 17 says that prove that the function f given by fx equals log of mod cos x is decreasing on this and increasing on this. Okay. This time we have an interesting function. We have modulus of cos x. Let's talk about fx equals log of mod cos x. So f prime x, what will that be equal to? Now log of something, the derivative is 1 upon mod cos x. What about the derivative of modulus cos x? Now derivative of mod x is slightly interesting. That is simply mod x upon x. Okay, where the derivative will not be defined when x is 0. Okay. So derivative of mod something will be mod cos x over cos x. This is what I'll get. But still, the chain rule says that derivative of cos x is also required. What is that? Minus sin x. Now, the important thing that I've used over here is derivative of mod x, which is mod x upon x, except when x is equal to 0. Right? And this is not difficult. This is pretty simple. You can observe it directly from the graph of mod x as well. The derivative gives you the slope, right? The derivative gives you the slope. This is a line y is equal to x. The slope y prime is simply 1. This is a line y is equal to minus x. The slope y prime is equal to minus 1. That's what you can observe, right? So 1 is actually equal to mod x upon x over here since x is greater than 0, right? This is equivalent to this. And minus 1 here is mod x upon x, which opens that mod x in this particular region will open as minus x. Minus x upon x, which will be minus 1, and this is 1. And that's what you can observe. And this is the way in which we can kind of deal with it. But this is what I get. If you observe cos x and cos x will get cancelled, and this is minus of sin upon cos is tan x. Okay. What about the first quadrant? For x belongs to 0 comma pi by 2. In this interval, tan x is positive, so minus tan x will be negative. This gives me f prime x will be less than 0. Okay, this tells me that f is decreasing in this interval. And was that what we wanted to prove? The function this given by this is decreasing on this interval. Yes, this is what we wanted to prove. That's the first part of the question. The second part says that for x belongs to, what do we have over here? 3 pi by 2 comma 2 pi. This interval. For x belongs to this interval, what do we have? In 3 pi by 2 comma 2 pi, this is the fourth quadrant. Tan x is negative, but minus of tan x will be positive. This tells me f prime x will be greater than 0, implies f is increasing over here in this interval. This is what we note. Since this is the fourth quadrant implies tan x will be negative. Therefore, f prime x, which is minus tan x, will be greater than 0. Okay, that's a complete solution and the proof of this question over here. Let's move on to the next one. The 18th question says that prove that the function given by fx equals x cube minus 3x square plus 3x minus 100 is increasing on R. Okay. So if you want to prove that this function is increasing, let's talk about the derivative. Let me write the function first. This is what we have. Fx equals this, which gives me f prime x is equal to what? 3x square minus 6x plus 3 is what I get. F prime x is this. Okay, we can take out 3 common. This becomes x square minus 2x plus 1. Okay, and this is 3 times x minus 1 whole square. That's what we have, right? So f prime x is this quantity, and do you observe that since this is a square quantity, this will be greater than equal to 0 for all x belongs to real numbers. For all x belongs to real, this quantity will be greater than equal to 0. Equal to 0 at only one unique point, that is 1. This is the derivative which is always greater than equal to 0. Therefore, this implies fx is increasing for x belongs to real. That's a complete proof. That's a simple question, yes, a pretty simple one, and that's a complete proof of this question with the help of this, right? That's a complete solution over here. Let's move on to the next question after this. The 19th question says the interval in which y equals x square times e power minus x is increasing. Okay, we are supposed to find the interval in which this particular function is increasing. Let's talk about this. This is y equals x square e power minus x. Okay, that's pretty interesting. We'll have to apply the product rule, yes. So y prime is equal to x square, let it remain constant, e power minus x, and since we want to apply the chain rule over here, the derivative of e power minus x is e power minus x. Okay, and then the derivative of minus x is minus 1 plus e power minus x will remain as it is, and the derivative of x square is 2x. Okay, so can I take out this e power minus x common throughout? Yes. What I'll get is minus x square plus 2x. Okay, I can take out another minus x common, yes. So this becomes minus x e power minus x times x minus 2. Do you observe that carefully? Yes. Now this has a critical point, this has a critical point, whereas e power minus x, now e power minus x, the sign is fixed. E power minus x, e power anything is positive. Okay. So this is always positive. We are not supposed to worry about the critical points of this. We are supposed to worry about only the critical points of this and this, which are 0 and 2. Okay. For values beyond 2, let's take for example 3. This is positive, this is positive, this is positive, this is negative. So overall we'll be having a negative sign. For values between 0 and 2, let's pick up 1. This is minus 1, which is negative, positive, positive and negative. So there are 2 negatives, it will overall become positive. For values below 0, we'll get minus 1. Let's take for example, this is negative, positive, negative and negative. There are 3 negatives, it will overall be minus. That's what you'll have, right? So that's the complete analysis, and the interval in which this is increasing. Increasing implies this interval. Here it is decreasing, here it is decreasing, increasing in this interval only. So 0, 2 is the interval, that is what I am looking forward to. That is option D, and that is the correct answer for this question over here. With this, we come to the conclusion of this particular exercise 6.2 from the chapter Application of Derivatives. Now this exercise once again was based on functions, increasing or decreasing nature of the functions using the first derivative, right? That's what we have dealt with over here, and I hope you have enjoyed watching all of these solutions with us.